Hello, everyone. Checking my levels, my audio levels, and 6 people watching. Okay, we're ready. Okay, good. So before I start, I should say what's on the test. So the test is on Newton's laws, okay, and solving problems with Newton's laws, which is what we're going to do today. There was also that brief section on Newton's Universal Gravitational Law and Kepler's laws, okay, and we'll do a problem on that today as well. And then energy, okay. Now, I won't be able to do a problem on energy today, but we did that just last week, so it's more important that we review some of the Newton's law stuff because that's further in the past. But if you do want to actually watch another energy problem, I'm going to do one for the Physics 101 tomorrow. And I'll make sure that if I use any calculus, I'll state it very explicitly, but I don't think I have to because they need calculus to prove the result, like the results, but not to actually solve problems. So I'll mention that in an email tomorrow. So if you want, you can even join that. But that's what that'll cover all the material on the test, and it's 28 questions long. I've timed it. You should be able to do it comfortably within an hour. But as I said in my email, I'll give you 2 hours. And there's some conflict, so I may have to open up the tests early for each of the sections. But it doesn't matter. Whenever you start it, you'll have 2 hours from the moment you start it. Okay, and so there it is. I'll give you more details, obviously, on the day of the test if there's exactly what times I'll start them. But that's it, okay? And you won't. The only other thing I should probably mention is that you won't actually see the answers, like what you got right and wrong, right after the test, and that's because there's some straddling, and some people might finish before other people. So uh, on Monday of the next week, I'll make it so that you can go back and see which ones you got right and which ones you got wrong. But you will see right away which what your grade is on that test. Okay. So all right, let's start here. Let me just take a look at the chat there. Yeah, everything looks good. And I lost my I lost my whiteboard here. Okay. That's been happening again today. All right, so my first question, I didn't actually fully write it out. I have a diagram which is going to explain it, but basically I have a double incline plane, and which you'll see in a second, and I want you to calculate the acceleration of that system, the direction of the acceleration, and also the tension in the rope, okay? So assuming no friction, okay? So here's the system that we're going to look at, okay? And it's a double incline plane. We haven't done one of these before. We've done, you know, uh, half incline plane. So you've got an incline plane here, and then you've got another mass which is just dangling off at the end. Okay, but this isn't that much more difficult, and so it's just a double incline plane. So you got a 7 kilogram here on a 40-degree incline, and you've got a 10 kilogram here on a 30-degree incline, and you're asked to find the acceleration of the system. Okay, so how do you start? Well, you start off by identifying all the forces for each one of the masses. So let's start with the 7 kilogram mass, and the first force we always start with is gravity. Now, technically, gravity is straight down, and it's equal to mg, which is m is 7 and g is 10. So we're rounding off to 10 as we usually do, and that would say 70 newtons down. But because the other forces are either perpendicular or parallel to the plane, what we usually do is we usually break up the gravitational force into a perpendicular component and a parallel component like that. And let's call this one M1 here like that. And let's call this one M2. All right. And there's actually two thetas as well. So we can call this one theta 1 and this one theta 2 down here like that. Okay. And to calculate the perpendicular component, that's the cosine. So the formula for this one is M1, because it's this mass right here. Okay. M1 times G times the cosine, and it's theta, but there are two thetas, so it's theta 1. It's this angle right here, okay? All right, so that's the perpendicular component. And the parallel component, well, once you get the perpendicular, it's m1g. The other one is the sine. So the perpendicular is the cosine, and the other one is the sine, like that, sine theta 1. All right? Okay, we'll calculate those on the other whiteboard in a minute, but that's gravity broken up into two components. Okay, now the other force is that's here is going to be the normal force like this, and we'll call this an Fn, but it's also number 1 because there's an Fn over here as well. Okay, so there's going to be 2 normal forces. Just to not confuse things, anything that has to do with the 7 kilogram mass, I'll put an extra 1 subscript. Anything that has to do with the 10 kilogram, I'll put an extra 2. Okay, so there's the normal force, and what other forces are there? Well, the third force is going to be tension up here like that. Okay, sorry about that. If you hear my dog barking, that's because the mailman just put something in my box. Okay, so this is FT like that. All right, and I'm not going to put FT1 and FT2 because it turns out that the tension is going to be the same on both of them, and that's because of Newton's third law. Okay, so Newton's third law says if one object pulls on another object, then the second object pulls back on the first object, same force, opposite direction. And FT over here, I guess I could draw it right now, is going to be like this. They're the same size, so that's why I'm going to call them both FT. They're not exactly opposite. And you go, well, does the third law really apply? Yeah, because of the pulley. The pulley is what changes the direction, okay? But other than that, the magnitudes are the same. All right, so for M1, we're done in terms of all the forces, okay? Now the values, I'll calculate those in just a second, but there they are, all right? And what about for M2 over here? Well, M2, it's the same thing, okay? So I won't write these formulas again because they're kind of annoying to draw in this environment, but there's going to be a perpendicular component this way. There's the parallel component that way, okay, perpendicular to the plane, parallel to the plane, and then there's also going to be a normal force like this, and this one we'll call Fn2, like that, okay? All right, now what you normally start doing now is seeing what values you can associate with these forces or components of forces, okay? Before I do that though, I'm going to notice that when there's no friction here, okay, there are no other frictional forces, you really don't need this component and that component, okay, or the perpendicular component and the normal force. Why? Well, because they cancel, okay? There's no acceleration perpendicular to the plane here, and as a result, the normal force this way and the perpendicular force of gravity that way, they have to cancel against one another. If the normal force were bigger, then there'd be an acceleration that way, in which case it'd be lifting off the plane, and it doesn't do that. And if the gravitational force, that's the perpendicular component of the gravitational force, were bigger, then it would accelerate that way. And it can't be doing either of them, so they would cancel, okay? So actually for question number 1, we don't even need those two forces. We know that they've canceled out. And the same thing is same thing over here. That one is going to cancel that one. Okay, so that's all we need from the diagram right now. Let's switch to the other whiteboard here like this, and let's start doing the calculations here. Okay, so I'm going to cut and paste stuff just so I don't make mistakes. All right, so over here, here's the analysis for M1. All right. And what's going on there? Well, okay, so the first thing is we do need the parallel component of gravity, okay? So parallel G, okay, so the parallel component of gravity. And for that one, it's the sign, okay? So this is a typical mistake that's made. I've seen students make this mistake before where they'll confuse the perpendicular and the parallel, and they'll call the perpendicular sign. No, the perpendicular is the cosine and the parallel is the sine. And I showed that in one of the pre-recorded lectures. I went through the geometry for that. So you don't have to rethink it. It's probably best that you just memorize perpendicular, cosine, parallel, sine. Okay, so now what? All right, so for the parallel component of gravity, for the 7 kilogram mass, it's m1g sine theta 1, okay? And m1 is 7, g is 10, rounding it off from 9.8, okay? Times the sine of 40 degrees, crunch that through your calculator, and it's 45 newtons, okay? So I'll write that in the diagram in just a minute, but there it is, okay? So we got 45 newtons, all right? Why did we do this? I mean, actually, maybe I should go back to the diagram right now. Okay, why did we do this? So if we take a look here at the diagram, we now know that this is equal to 45 newtons, okay? So we've got that one. We don't need these two because, like I said, we don't, they cancel. We don't need them for question number one, okay? But we also have this tension here like that, all right? And the tension there is going to be competing against the force of gravity that way, okay? Now, you're not sure which one's going to win, all right? And so maybe we should just leave that off for a minute and say, I'm not sure which one we're going to win. Let's look at this one here and do the same kind of analysis for this one. And once we do, you'll see that actually the acceleration is going to go this way for that one and this way for that one. Okay, so at this point you don't know that, but let's look at uh, uh, the same kind of analysis. We're not complete here, but let's do the same kind of analysis for number two. Okay, and over here got M2 like this. Let me just cut and paste that in here like that. So just look at this part right now, okay? And then for M2, we're going to do the same thing, where the parallel component is going to equal M2G sine theta 2. And so substituting in M2 is 10, G is 10, sine of 30 degrees. Sine of 30 degrees, by the way, is a half. So 10 times 10 is 100, multiplied by half is 50 newtons, okay? So let's draw that one in there, all right? Okay, so over here, we know that this force over here is going to be 50 newtons, all right? And, again, the perpendicular forces are all out of the picture for both the 7 and the 10 kilogram. The reason we know that the acceleration is going to be in the direction that I showed you is because if you compare this force here with that force there, okay, you see that gravity, at least the parallel component of the gravity, wants to pull the 10 kilogram down with 50 newtons, and it wants to pull the 7 kilogram down with 45 newtons. Which one's going to win? Okay, well, it's pretty obvious that the 50 newtons is going to win. Okay, so that says that this is going to be winning over that one. Okay, and that's what's going to determine that the acceleration will be in the direction that I showed you. All right. Now, I did that just to show you that there's a few ways that you could get the direction for the acceleration. Even if you make a mistake, even if instead of this, oh, I guess, how am I going to rub this off? Oh, there we go. All right, I guess I got to rewrite the 15 newtons here. Okay. Even if you had made a mistake, suppose that by accident you said, oh, the acceleration is going to be up that way, all right? Even if you did that and you worked through it, you would get a negative answer for the acceleration, and then you go, oh, it's negative. It must have been in the other direction. I'll show you that towards the end. But, the reason I jumped to this one rather than completing, everything for M1 first, is just to show you that this is going to be 50 newtons, that was 45. So the 50 newtons is going to win, and the acceleration is going to be in that direction right there. Okay? Let me see what's going on in the chat here. All right, well, everyone's quiet, so no questions. All right, so when we do that now, we're going to make use for each one of them, for each of the masses, we're going to make use of Newton's second law. And what does Newton's second law say? It says that F net is equal to ma. So when we apply that to m1, that's going to say that F net for number 1 is going to equal m1 times a. Okay, and when we do it for number 2, that's going to say that F net for number 2 is going to equal m2 times a. All right, and how do you get F net? Well, F net, to get that, that's got to be a vector sum. We're going to have to do a vector sum. But the vector sum is very easy because that's why we kind of resolved everything so that it forms that cross. And that's because all you have to really worry about is this 45 here and that ft there. Okay, they're competing against one another, and then you ask yourself, well, which one's going to win? Well, ft uphill has to win, and the reason is that if this is accelerating downhill, the 10 kilogram is accelerating downhill, the 7 kilogram is accelerating uphill. Okay, and that means that that ft must be bigger than 45 newtons. All right, so when you go to calculate F net, and F net means add them all up. So we're going to add up all 4 forces. Well, 2 of them cancel, so they're out of the picture. So the only 2 we have to add is this one and that one. And Ft is going to be bigger, so we're going to do that F net is going to be Ft minus 45. Okay, so over here, for the vector sum to get F net, it's going to be Ft, which is trying to pull it uphill and is winning, minus the 45, which is trying to pull it downhill. Okay, and so great. F net, we can now write F net for number one. We can now write as Ft minus 45, and there it is. So this is F net, but now written in terms of the sum of the forces. Okay, and then over here we have m1 times a, and m1 is 7, and so we have that. Okay, so this is Newton's second law, where this side we got by doing what net means, adding up all the forces, and we found that it's Ft minus 45 newtons. Okay, and this side is ma, and m, I told you what m is, it's 7, and so you get that F net here is equal to ma, and you can't go any further. Okay, if this was a problem with just one mass, you could solve for a at this point, because you would have all the forces. I mean, I'd have to give you all the information to get all the forces, but you can't solve this because you don't know what Ft is. Okay, and this happens when you have two masses. The rope between them has a tension in it. You don't know what that tension is. Okay, you know that it has to be bigger than 45 to pull this one uphill. All right, and in a minute you're going to see that it's going to be less than 50, because otherwise the gravitational force would pull the other one downhill. You'll see that in a second, but you don't know its value. Okay, and so you have one equation here with two unknowns. All right, so let's do the same analysis now for the other box. All right, so for the 10 kilogram box here, again, the perpendicular components are out of the picture. They're gone. Don't even pay attention to them. You're really just looking at this force here and that force there. Okay, and we know that the 10 kilogram is accelerating downhill, so the 50 Newton must be the bigger one. All right, so F net in this case is going to be 50 minus Ft. All right, over here it was Ft minus 45, but here it's going to be 50 minus Ft. 50, the 50 newtons has to be bigger than the Ft, otherwise it wouldn't accelerate downhill. Okay, and actually this is kind of nice because it tells you something about how big Ft has to be. Ft has to be bigger than 45 so that the 7 kilogram accelerates uphill, and it has to be less than the 50, otherwise the 10 kilogram would not accelerate downhill. We'll see that when we get to the end. Okay, but for now, F net for the second box here, it has to be 50 newtons minus the Ft. All right, so let's switch back here. And you can see that I wrote that F net for box number 2 is going to be the 50 newtons downhill minus Ft uphill. Okay, and that's got to equal ma, or m2a. All right, this equality here, that's just the vector sum. Okay, so we get from F net 2 equal to 50 minus Ft. That's because we just added up all the vectors. Okay, the second equality here, that one, that is because of Newton's second law. Okay, so two things going on here. One is the vector sum for F net, and then set that equal to ma. That's Newton's second law. All right, so taking this equation here, I just dropped the units so that it's not as confusing. I get 50 minus Ft. M2 we know was 10 kilograms, and so we get 50 minus Ft is equal to 10a. Okay, and that we can call equation number 2. Okay, there's really nothing more you can do with either equation 1 or 2 by themselves, but together you can solve them because you've got two equations and two unknowns. Okay, now the technique that I showed you works for these kinds of problems. It doesn't work in general, but it does work for these kinds of problems, and that is you just add the two sides. Okay, so let me cut and paste that solution here like that. Okay, so solve for F A and Ft in equations 1 and 2. You just put the two equations together. Okay, so there's equation number 1, there's equation number 2. And what you do now is you just take the left-hand side from equation 1 and you add it to the left-hand side of equation 2. Here it is. Here's the left-hand side equation 1 plus left-hand side equation 2. And you'll notice that this is positive Ft and that's negative Ft, so the Ft's cancel. All right. Like I said, this doesn't happen in general when you have two equations and two unknowns, but it does happen in these problems. So you might as well make use of this technique. So again, left-hand side of the first equation plus left-hand side of the second equation. Well, that's got to equal right-hand side of the first equation plus the right-hand side of the second equation there, like that. Okay. If you want to know what's going on there here, just a quick little aside. If I have like 3 is equal to 3, and I have like, I don't know, 5 is equal to 5 like that. Well, obviously if I take 3 plus 5, right, where I add the left-hand sides, that's going to equal 3 plus 5 if I add the right-hand sides. Okay, so that's all I'm doing here is I'm just saying, look, if this is equal, if that equality holds and that equality holds, then the sum of their sides has to also equal. Okay, so we have that, and the FTs cancel out. It's negative 45 plus 50, and so that just leaves you with 5 on the left-hand side. And over here we have 7 plus 10a, and so that gives you 17a on the right-hand side. So you have 5 is equal to 17a. 5 divided by 17 is that number there, and so that gives you the acceleration. Okay, and I asked also for the direction. Okay, so what's the acceleration and what's the direction? We already have that direction. Okay, and if you go back to the diagram here, you can see that the 10 kilogram is accelerating downhill, and of course, as a result, the 7 kilogram has to be accelerating uphill. All right, so whoops, wrong. There we go. Okay, and it gives us the acceleration and the direction. All right. You say, how do I solve now for ft? You could pick either one of those two equations and substitute a in for that, and you'll get ft. Okay, so I guess I said just use find ft using equation number 1. Here's equation number 1 rewritten. Whoops, I lost the 7a there like that. Okay, so there's equation number 1. Ft minus 45 is 7a. I just copied from above. And now you see we know a. A is this value right here. So if I put a in there and I solve for ft, so I've got ft minus 45 is 7a. So that means that ft is going to equal 45 plus 7a, but the a we already know, and then just plugging it all in, I get that ft is going to be 47.058, or that throughout the course we've been rounding off to 3 significant figures, so this turns out to be 47.1 newtons. Okay, and there's the tension. So we got both the acceleration and the tension, and that answers the question. If you go back to the diagram here like that, we could even write it in there. We can now see that ft here is 47.1 newtons. That, and this ft is the same. Okay, well, remember a minute ago I said, well, this ft has to be bigger than that so that the 7 kilogram mass accelerates uphill, and sure enough we got 47.1, okay, which is bigger than 45. Okay, so yeah, ft is bigger than the 45. All right, over on this other side we have the 50 pulling it down and 47 pulling it up. And again, the 50 is bigger than the 47, because if it weren't, well, then the 10 kilogram would not be accelerating downhill. So everything turns out very consistent. Okay, so that answers question number 1. And let me see if you guys have any questions in the chat here. Oh, it looks like you're okay. Everyone okay so far? All right. Okay, well, let's go on then to questions 2 and 3. Okay, and what I did in question number 2 is I said, same situation, but now we're going to have static friction. Okay, and I'm only going to put the static friction on the 7 kilogram box. So the 7 kilogram box has static friction. So that's why I said assume only the 7 kilogram box has static friction. The 10 kilogram does not. Okay, the 10 kilogram does not. I could have added it there, but then that would make life pretty complicated. Okay, so I said, you know what? Let's just make the 7 kilogram have static friction, and I want you to calculate how much static friction there is, and I also want you to find the range for the static friction. So let me actually show you the formula that for the coefficient of static friction. It's actually not an equality, it's an inequality, and here it is. Okay, like that. All right. Now let me take out the number 1 there. It's I'll show you why that 1 was in there in a minute. But let's just look at that equation. It's an inequality. Okay. Now when we do the analysis, we'll actually get Fs. That's one of the questions, how much static friction there is. We'll get the normal force. Okay. But then when we plug it in, we get this inequality, and that doesn't specify what mu s is. It just specifies a range for mu s. Okay. And just to show you what I mean by that, I mean, suppose you have this inequality here. Okay, and so this inequality basically says that x is bigger than or equal to 6. That doesn't tell you what x is equal to. It just says that it's bigger than or equal to 6. Okay, so x could be 7, X could be 10, X could be 20, X could be 20.5. You don't know. All you know is that it's bigger than 6. That's the only thing that this is telling you. Okay, and the same thing happens with mu s. It doesn't, like this formula here for mu s, it doesn't tell you what mu s is. It just tells you the range. Okay, and so that's why the way I asked the question here is I said, what is the range for the coefficient of static friction? All right, and so as you might guess, there's going to be a question like this on the test. And I'm going to say, what's the coefficient of static friction? And the answers are going to be greater than this amount, less than this amount, something like that. Okay. So that you get out of this equation right here. Okay. Well, let's switch back to the diagram. Okay. And let's see if we can figure out what the static friction is. All right. So let me try to erase stuff here. Let me see if I can just go backwards and erase stuff. Erase stuff. Actually, I think this is good right now. Okay. Um, so if we did this, we'd have this diagram. The only difference would be what? Well, there's friction right along here, right? There's friction along there. And so there has to be a force of friction on the 7 kilogram. And which way would that force of friction be? Well, the 7 kilogram wants to be pulled uphill. And so if something is going to prevent it from going uphill, it has to be a force of friction downhill like that. Okay, and so that force right there, I'll write it over here, that's Fs. At this point, we do not know how big Fs is. Okay, in fact, that's the first question, find Fs. Okay, and you say, well, how do I do that? Well, in this problem, A is equal to 0, like that, and A is equal to 0. So in some sense, you kind of work backwards from the previous problem. In the previous problem, we found all our forces, and then, we worked through Newton's second law, and we got the acceleration. This time, we know the acceleration. We know that the acceleration is 0. So what does that mean? Well, Newton's first law says if the acceleration is 0, what does that tell you about the forces? They have to all add up to 0. Okay? So we already know that the perpendicular forces on M2 add up to 0. But we didn't say anything about the parallel forces, okay? Now, if this is 50 newtons here, okay, what must this one be? Well, if the acceleration is 0, those two had better cancel. Because if the 50 newton is bigger, then it's going to accelerate downhill. If Ft is bigger, then it's going to accelerate uphill. If it's neither going uphill or downhill, then the two have to be equal to one another. And so you can say that Ft here is going to equal 50 newtons. Okay, so you didn't really need a formula or anything like that. You didn't have to like invoke any law. You just know that, well, I guess you did. You invoked the first law. You just said, you know what, no acceleration, so all the forces have to cancel, so that force has to cancel that force right there. All right, great. Now, if this is Ft on this side, well, guess what? This is also 50 newtons on that side, because Newton's third law says the tension in the string is the same all the way through it. Okay, so that's 50 newtons, that's 50 newtons. Again, the perpendicular components cancel out here. So now you're going to say, okay, well, let me compare this to these forces down here. Okay, well, we have 50 newtons pulling up and only 45 newtons due to gravity pulling down. We have 45 down, but we need 50. Okay, and that's a difference of 5, right? You got 45, you need to get to 50, so you need 5 more newtons. And you wonder, where do those 5 more newtons come from? And that's the friction. Okay, so the friction is combining with the gravitational force downhill, the parallel part of it downhill, and the two are competing against the 50 uphill. Okay, and so you can conclude that Fs here has to be 5 newtons. All right. So static friction is kind of funny, because what you have to do here to reason out your static friction is you basically have to say something like this. What does the static friction have to be such that it doesn't move? Okay, well, once again, if you've got 50 up and you've only got 45 down due to the gravity, you better find another 5. Otherwise, the 50 is going to beat the 45. And the answer is these two together, static friction plus gravity down, they successfully counterbalance the 50 M. And so the static friction must equal 5 newtons, okay? And so that's how you get it. That's how you get the static friction, all right? So over here, we can write down and say, all right, we know that the force of static friction has to equal 5 newtons, okay? Because A is equal to 0. And the direction, because I asked not only how much static friction, but in what direction, it's downhill at the 7 kilogram mass. Okay, so that answers this part right here. So that's you might find it strange that I didn't even use a formula to find the static friction, and you don't use this formula here to find static friction. Okay, um, you simply think it through the way I just did, and you say static friction is whatever it needs to be such that the acceleration is 0, or such that all the forces add up to 0. Okay, and as you saw, you had 45, you needed 50, so that extra 5 that came from the static friction. All right, static friction will simply adjust itself. It'll grow, it'll shrink to be whatever it needs to be, such that the net force is 0. Okay, great, we've got that one. Now, this is actually static friction only for the 7 kilogram mass. That's why I originally had an Fn1 here, okay? Because if we go back to the diagram here like that, it's the normal force for the 7 kilogram mass, okay? Well, we don't know how big the normal force is, okay? And we didn't calculate it before because we didn't need it, but now we do. We need it because that comes into the formula, and we can get it because this force here has to balance against that force there. So if we calculate this one, the perpendicular component of gravity, then we have that one, the normal force. Okay, so let's do that next. All right, I'll copy and paste that. All right, right here. So the normal force for M1, that's going to equal M1g cosine theta 1, all right, the perpendicular component of gravity for M1, okay, and just plugging in the numbers, M1 is 7, G is 10, and cosine of 45 degrees, that gives you 53.6 newtons, okay. So now we have the static friction, and we have the normal force, and we could just use that equation right there to work out what the range is for the static friction. And I'll just copy and paste that right there like that. Okay, so there's the Fs and Fn substituted, and it turns out that the coefficient of static friction has to be bigger than 0.0933. There's more decimals, but I rounded it off. Okay, it doesn't tell you what mu s is. Okay, it just tells you it has to be bigger than that. If mu s were smaller than that, then you wouldn't be in a situation of static friction. It would break free and it would start to move. Okay, the blocks would start to move, and I'm telling you it doesn't do that. Therefore, whatever that mu s is, it has to be bigger than 0.0933. Okay, so there you go. There's a static friction. All right. All right, let me take a quick peek in the chat here. All right, looks good. 5 people watching. All right, let's go on to question number 3 here. So question number 3, what I tried to do with this problem is I tried to cover all bases. Okay, if you understand this problem, you'll have no problems on the test because this covers everything we studied in terms of like solving or applying Newton's laws to these kinds of problems. Okay, so the only other thing we really need to look at is kinetic friction, and rather than applying the kinetic friction to the 7 kilogram mass, I said, you know what, let's apply the kinetic friction to the 9, sorry, to the 10, and pretend that there is no static friction on the 7 kilogram mass. Okay, so assume only the 10 kilogram mass has a coefficient of friction of 0.03. Okay, and by the way, that number 0.03, I don't know if it was for your class or one of the classes. I accidentally chose mu k, which was too big. Mu k has to always be smaller than mu s. Okay, now technically this is mu s for the 7 kilogram, and now we're talking the 10 kilograms. So we're comparing apples and oranges a bit. But, roughly speaking, it would be about like in the same ballpark. So mu k has to be smaller than that. If mu k were bigger than mu s, you'd be in trouble because it wouldn't even start to move. Okay, so it'd be kind of a contradiction. How can it be a mu k, a coefficient of kinetic friction, if it's not even going to move? Okay, because if mu k is bigger than the minimum US, well, then it's not going to move because mu-s, if you've satisfied the criterion for mu-s, it's not moving. So mu-k has to always be less than mu-s. All right. So there it is. I simply chose a mu-k of 0.03. Okay. And my first question is, how much kinetic friction is there and in what direction? Okay. Remember, now it's only on the 10 kilogram mass. And what's the acceleration and what's the tension? All right. Well, let's switch back to the diagram here, and let me see if I can erase back far enough. Otherwise, I may have to just redraw everything. Looks like it's working. Yeah. Okay, good. Okay. So here's the diagram when there's no friction at all. Okay. And now there is going to be friction, but this time the friction is right here. It's with the 10 kilogram mass, and it's kinetic friction, so it will be accelerating downhill. Okay, but it's just going to be accelerating downhill less than it was in question number 1. Okay, and so now you say to yourself, well, what direction does is the friction going to be? Well, if it's moving downhill, then the friction, the kinetic friction, is going to be uphill like that. I think that's pretty obvious. Friction is always in the opposite direction than it's moving. So if it's accelerating downhill, its velocity would be downhill, and the frictional force would be uphill. I don't know how big it is, but it's definitely going to be uphill. Okay, and now we're going to be in a situation where Ft and Ff are going to combine together to compete against the 50 newtons. The 50 newtons down is still going to win, but now it's the 50 newtons isn't just competing against Ft, it's competing against Ft and Ff together. Okay, and you say, well, how do I get this FF here like that? Okay, because you're going to need it. All right, FT you don't have, but that's okay because you're going to get 2 equations and 2 unknowns like we did above. All right, and so we'll be able to solve it, but we do have to have a number for FF. And you say, how do you get that? So it's like this. For kinetic friction, it's not an inequality. For kinetic friction, it's actually an equality. It's this equation here. Okay. And the reason I got 2 there, so it's FF, which is the force of friction, divided by the normal force Fn. Fn, the reason I put a 2 there is because it's for mass number 2. Okay. In general, the equation just looks like that. Okay. So it's FF divided by Fn. But in this particular case, we're talking about mass number 2. So there it is. All right. Notice it's an equality. So even though these 2 equations look very similar, that one looks very similar to that one. They're like worlds apart because one of them being an inequality, you can't use it to solve for anything there. Okay, all you can use it is to set limits. But for the second one, for mu k, yeah, you can use it to solve for ff. Okay, and here's how you do that. If you just rearrange this, you could say, well, ff is going to equal mu k times fn, like this. And the next thing you're going to say is, well, I have mu k. I told you that was 0.03. Do you have Fn? And no, but you can get Fn. Okay, why? Well, look at the diagram again. Fn number 2 here, this Fn here, has to balance against the perpendicular force right there. Okay, and so if you can calculate that one, then you got that one. Okay, and you can, because this one is going to be, it's kind of like this formula right here, but instead of for M1, for M2. Okay, and so let's switch back, and I've got this equation right here. Okay, so basically the normal force for number 2 is going to be equal to the perpendicular force of gravity for number 2. Whoops, I guess I should put a theta 2 there. Okay, like that. Okay, and then if you plug in the numbers, M2 is 10, G, we've been rounding up to 10. Okay, cosine of 30 degrees, and you crunch that through your calculator, and you get that the perpendicular component of gravity is going to be 86.6 newtons, and also the normal force is 86.6 newtons. Okay, let's actually write that into the diagram. Okay, just so we can see it. Probably don't need to, but let's do it anyhow. So this is going to equal. Actually, let's do the blue here. This is going to be equal to 86.6 newtons. And the normal force has to balance against it. So the normal force here has got to equal 86.6 newtons, like that. Okay. All right. What about that force of friction? Because that's where we were heading with all of this. Well, now we can just use this equation here, right? So, we've got that. But now we can write from UK, we can write 0.03. And for FF, we can write 86.6. And whoops. And what does that give us? That gives us this number right here. All right. So it gives us that the frictional force is 2.598. Okay, I'm gonna just I'll write it in the diagram. Let me just round it off to 2.6 for the diagram. Okay, it's annoying to write all those decimals in there, but on your calculator you can carry them all. So this here is going to turn out to be 2.6 newtons. Okay, like that. So once again, this 50 newtons, it's competing against the 2.6 and FT. Okay, and so F net is going to be 50 minus the FT, but also minus the 2.6. Okay, so over here, uh, F net for number 2. I guess at this point, what I should probably do is say, what, we're doing the free body diagram for M2, which is the 10 kilogram. Okay. All right. So F net, what's that got to equal? So it's the 50 newtons downhill minus FT uphill, but also minus the frictional force uphill, like that. Okay. And I guess I can just reduce that a little bit. So that's going to be like 50 minus this number right here. All right, that's going to equal this minus FT. Okay, so all I did was just simplified here. I just took 50 and I subtracted 2.598 from it. Okay, so the 50 minus the 2.598, that gives me 47.402, and I still have the negative FT. Okay, and that's the vector sum. Okay, so that sums up all the forces and gives me the net force on number 2. Okay, what's that got to equal? So this is a point where students kind of get confused. They say, I've done that vector sum. What did I do it for? You did it so that you could set this equal to MA. Well, it's M2A, like that. And we know that M2 is 10. And so we've got this equation right here, like that. Okay? So we can call this one equation number 1. All right? And we can't go any further with that. Why? Well, because we don't know FT. And we're going to find FT because we're going to do the same analysis for M1. Okay, but you know what? We did that analysis already. Because if you go back here, M1, there's no friction. So what do you have? Well, you have FT uphill beating the 45 downhill. So F net here is FT minus 45, and that's got to equal 7A. And that's exactly what we did for question number 1. Okay, in other words, nothing changes. In terms of the analysis. The numbers will change for FT, it'll change. You'll see that at the end. But, the analysis is the same. So I'm just going to cut and paste that from up here, okay? So for M1, we did this analysis right here, all right? And we can just bring that down here like that, okay? All right, so actually we don't need this part here. And you know what, let's just put the vector sum and Newton's law together. I guess I'm rubbing off too much here maybe. But basically this is Newton's second law and so we want F net there, which is the Ft minus 45. There it is. And then on the other side of Newton's second law, we want M1A, and that's the 7A, okay? And so we get this equation here. I guess we got to call it equation number 2 at this point, okay? So we've got one equation for M2 and another equation for M1. And the equation for M1, like I said, it didn't change form because there's no extra forces, okay? And so how do you solve it? So it's the same thing as above. So let me see here. I've got it already solved. Whoops. You know what? I've been cutting and pasting into the wrong thing. Let me fix that for you guys. I was cutting and pasting into the wrong one. Okay? Let me just, it's a quick fix. Yeah, I apologize. Let me see here. No, I wasn't. No, I wasn't. I've got two things open. That's I'm getting confused here between all my windows. Okay. No, I'm good. I just have to solve these two together. Okay. And here's the solution right here. Okay. All right. So here's equation number 1. Okay. And here's equation number 2. And we add left-hand side here to that one, and we get this. And you'll notice again you get negative ft plus ft, so they'll cancel. And then 10 plus 7 is 17. And so you get, just the 47.402 minus 45 on the left-hand side, 10 plus 7. And it reduces to this, and you get that, okay? So actually you get a bunch of decimals, and I just rounded it off, okay, like that. All right. So there's the acceleration. And I asked for the direction as well. The 10 kilogram is going downhill. The 7 kilogram is being pulled up here. The same thing as in question number 1. Okay. Now, just to make sure that we're doing this right, okay, you might want to compare with the answer that you got for number 1. And for number 1, without friction, we had this answer right here. Okay, so I'm going to paste that in there like that. Okay. And you can see that with friction, we're getting, 0.141, and without friction we had 0.294. So as you expect, with the extra friction, you're going to have less acceleration. Okay, it's still going to go downhill because it's kinetic. And kinetic means it's still moving, but it's going to be moving less than it was moving in part 1 because it's been slowed down by that extra, 2.6 newtons worth of friction on the 10 kilogram block. All right, so I also asked for the tension, so let's do that. And for the tension, same thing as above, use either equation number 1 or 2, and you can solve for that. And so over here, using either equation number 1 or 2 to solve for the tension, you just plug in. I decided to use number 1 just because it seemed a little bit easier to use. Oh, sorry, number 2. I just used equation number 2. So there's equation number 2 just repeated. And, I've got Ft minus 45 is equal to 7a. Bring the 45 to the other side. In other words, add 45 to both sides. And I have this. And then I could substitute in for a because we just calculated it. That's the 0.141. And that gives me, that the tension with friction is 46 newtons. Okay. If you compare that to what we got in part 1, okay, which had no friction, there we had that the tension was 47.1. So now we have less tension, okay? And you might wonder, is that right? Do we have less tension with friction? Yeah, let me show you why. Let's go back to the diagram here, okay? So whatever the tension is, look at the 7 kilogram, okay? So just concentrate on the 7 kilogram. Whatever that tension is, okay, this tension is what is competing against that there, okay? And when we subtract the two, we have to get a smaller net force than we did before because we have a smaller acceleration. And so the difference between the 45 and Ft has to be smaller in this case than it was before, okay, because you got a smaller acceleration. Smaller difference between Ft and 45, smaller acceleration. And so, yeah, before we got 47, but this time we're getting 46 newtons, okay? It's still bigger than 45, which means it's going to accelerate uphill. It's just going to accelerate uphill less than it did in part 1, which was 47.1. Okay, so and that makes sense. Everything's moving slower, so it's got to accelerate uphill slower than it did before. All right. And well, there it goes. Okay, so why reason that out, and just to check. It's just a check on your, make sure everything is consistent. Okay, so this solves everything that I wanted to do with Newton's laws. Let me see if you guys have any questions in the chat here. Okay, so uh, the last part of it, let's do some questions on uh, Newton's universal gravitational law and Kepler's laws. Okay, so over here I have a question, two parts, 4A and 4B. What is the gravitational force between two 1 gram masses that are 1 centimeter apart? Okay, so Newton's universal gravitational law says that between any two objects in the universe, there's an attractive force. But if the objects are small, and by small, really what you mean is small relative to planetary sizes, okay, which is almost everything in our everyday life, okay, then the gravitational force is going to be small, okay. That's why, yeah, there's a gravitational force between you and the car, okay, or between you and the walls. But it's not like I feel the walls pulling me back, because there's some strong gravitational force. It's so small that it's barely measurable, okay? The only time gravity starts to really pick up is when the objects are about the size of a planet, okay, or an asteroid or something like that, okay? But certainly if an object is tiny, like, you are, or like, your car is, it's a very, very small number, okay? It's almost unmeasurably small. All right, but it's still there. It's still there. Okay, so so that's the point of this question. I said, let's actually calculate that gravitational force between two 1 gram masses that are only a centimeter apart. Okay, the formula for that, this is Newton's universal gravitational law, is this one right here. Okay, so here's the formula, like that. Oops, that's the constant. Let me give you the formula. Right here. There's the formula. Okay, so this is this formula right here is Newton's universal gravitational law. Okay, and the constant in it, the capital G, that's this value up here. I would never ask you to memorize a constant. I mean, our tests are open book. I guess you could Google for this number, but I would give it to you if you needed it. I would give you any constants on a test if you need it. Okay, so what is the formula? It's G, this universal gravitational constant, times the first mass multiplied by the second mass divided by the distance between the two masses squared. Okay, and it's actually like the distance between the middles of the two masses. All right, and so if we plug in all the numbers here, we got to convert to MKS. Okay, here's what we get. Okay, so for the capital G, we plug in the universal gravitational constant. Okay, for M1 I told you was 1 gram. Okay, we have to work in MKS, so you got to convert from 1 gram to 1 kilogram. A gram is a thousandth of a kilogram, so it's going to be 0.001. Okay, so this is the first 1 gram mass. Here's the second 1 gram mass. They're both the same size, 0.001 grams, and they are 1 centimeter apart. Okay, and so here they are 1 centimeter apart. For R, we're going to put in 0.01. Okay, 1 centimeter, convert that to meters, is 0.01 meters. All right, and so just crunch this through your calculator and be careful, because there's a lot of possibilities of like entering the numbers incorrectly, but you get this number here, okay, which is 6.67 times 10 to the minus 13 newtons. 10 to the minus 13 is unbelievably small. Like, 10 to the minus 9 is a billionth. Okay, 10 to the minus 12 is a trillionth. And 10 to the minus 13 is a tenth of a trillionth, okay, of a newton. And a newton is already very small. That's just unimaginably small. Okay, the force of gravity between these two 1 gram masses is so small that it's not measurable. It's unmeasurably small. Okay, and so there you go. That's why you don't experience the force of gravity, in your day-to-day life between you and other objects. You experience the force of gravity between you and the Earth, because the Earth is big, but not between you and like your car or like the walls or whatever objects are around you. You just don't experience that force. Okay, so just to contrast this, when is the force of gravity significant? Well, I asked, what is the force of gravity between the Earth and the Sun? Well, to do this, what do you need? Well, if you look at the formula up here, you're going to need the mass of the Earth, you're going to need the mass of the Sun, and you're going to need the distance between the Earth and the Sun. Okay. Again, I would never ask you to memorize numbers like this. Okay. I just Googled for them before the class, and here they are. Okay. The mass of the Earth is that number right there. It's 10 to the 24, which is unimaginably big. Okay, the mass of the Sun is even more unimaginably big, if such a thing is possible. Okay, the distance between the Earth and the Sun, I called it RES, Earth Sun. Okay, again, this is the way Google gave it to me. It gave it to me as 148.65 million kilometers. Okay, now the mass of the Earth and the Sun, they're already in kilograms, and that's MKS. This one isn't. This one is in millions of kilometers. Well, million is 10 to the 6. So you've got the 148.65, okay? Million is 10 to the 6. Kilometers we want to convert to meters, and a kilometer, 1,000 kilometers is a meter, so the kilo, I'm going to replace that with 1,000. This is how the 148 million kilometers translates into meters, okay? So a little bit complicated. This is the million part, okay, and the 1,000 here, that's the K part, and then you're down to meters. All right, and then just substituting all those numbers into that equation, g m1 m2 over r squared, and crunching it through, you get this number here, which is 3.59 times 10 to the 22 newtons. And 10 to the 22 is so big that's unimaginably big. But of course, we're not talking about small objects anymore. Now we're talking about, the Earth and the Sun. Okay, and so that's the force that's keeping this huge thing, the Earth, going around the Sun. It's a huge force. Okay, so when it comes to planetary sizes, yeah, the force of gravity is big, but when it comes to small objects, it's very small. Okay, all right, so that's Newton's gravitational law, universal gravitational law. Okay, the other ones were Kepler's laws, and Kepler's law 1 and 2. There's not much I can ask on them. I mean, I can't ask you to solve problems. You should just know what they are. The first one says that the shape of the orbits, planetary orbits, are ellipses, not circles. Before Kepler, everyone thought they were circles. I don't know. They were stuck on circles, and Kepler said no, they're actually ellipses with the Sun at one of the focal points. Okay, and the mathematics of ellipses too hard for you guys to work with. So there's no problems I can really ask you for number one. You should just know that. You should just, like, if I asked what shape are orbits, the answer is ellipses. Okay, they're not triangles, they're not circles. Okay, they can be. Well, now I got to be careful. They can be circles because the circle is a special ellipse, but they're not in general circles. Okay, in general they're ellipses. A circle is just a special kind of ellipse. A bit of a subtle point, but I better be careful. Okay, the second Kepler's law is also kind of complicated. It says that, if there was a line from the planet to the Sun, the amount of area that line would sweep out is an equal amount in an equal amount of area is swept out in an equal amount of time. And that's just a brainful. You're like, well, what does that even mean? Basically, it turns out that the closer the planet is to the Sun, the faster it moves along its orbit. Okay, so because the orbits are ellipses, there's a time when the planet is close, and there's a time when the planet is far away. When the planet is close to the Sun, it's moving fast. When the planet is far from the Sun, it's moving slow. The third law, though, I can ask problems for. And the third law basically says that this ratio, r cubed over t squared, is the same for all the planets, where r is the distance from the Sun to the planet. That's r. T is the period. It's the time it takes the planet to go around the Sun once. Okay, in other words, a year. Like the Earth year is 365 days, but other planets have different length years. Okay, so if you do r cubed over t squared, it's the same for all the planets. Okay, so let's take a look at question number 5, because it's actually Kepler's third law problem, and it says an asteroid takes 565 Earth days to go around the Sun. Okay, how long does it take the Earth to go around the Sun? Well, 365. But this asteroid takes 565. It's a bit further from the Sun than the Earth, but we want to find out how much. So how much bigger is its orbit than the Earth's orbit? Okay, and no, I guess I said that wrong. How much bigger is its orbit than the Earth's orbit? Whoops. So just get rid of this part here. Okay, there we go. And I want you to answer as a percentage. Now you say, well, I'm going to need the Earth's orbit. Not really. You don't need the size of the Earth's orbit. All you need is how much bigger it is than the Earth's orbit. And so you know what we're going to do? We're going to say that the Earth's orbit is 1 unit. Okay. In fact, it's called 1 astronomical unit. But you don't even have to worry about it because all you're going to compare is, this orbit, how much bigger it is. Okay. So let me write down Kepler's third law. Okay. So here is Kepler's third law right there. Okay, and it kind of looks funny on my whiteboard here, but let me just explain it. So we got radius of the Earth and the period of the Earth. So that little subscript there, E, means Earth. Okay, and so what is this? What is this ratio right here? This ratio right here is R cubed, R to the third power, divided by T squared. Okay, and if you calculate R cubed divided by T squared for the Earth, that's going to equal R cubed divided by T squared for the asteroid. Okay? So there you go. Now what? Well, now we can put numbers in here. For the Earth's orbit, well, you know what? We're just going to put 1 in there. And again, the reason is all we want is the percentage bigger. So we're going to get a number out for the radius of the planet here. Sorry, the asteroid. Okay? And it's going to be bigger than 1, and all we want to know is how much bigger than 1 it is, like percentage-wise, how much bigger than 1 it is. Okay, so that's why you don't have to put in the Earth's orbit. If you did, it would still work out just fine. It's just at the end you get an answer for RA, and you'd wind up dividing it by the answer for RE anyhow, or the number for RE. And the reason is because you want to know how much percentage-wise bigger it is. Okay, and so you know what? If we just want to do a comparison of how much bigger the radius of the orbits are, just put 1 in for the Earth. Okay, I hope that's not too subtle, but this will work. Okay, and then for the excuse me. Oh, I apologize for that. I would have muted if I'd known it was coming, but so the Earth's orbit period is 365 days, so 365 squared like that. Okay, so there's the Earth's orbit normalized to 1, so 1 astronomical unit. Okay, the period of the Earth's orbit is 365 days. What's that got to equal? Well, that's equal to the radius of the asteroid cubed. We don't know how big that is. That's what we're solving for. Divided by the period of the asteroid's orbit, which we do know is 565 days, squared like that. Okay, now what? Well, let me multiply both sides because I want to isolate R cubed. Let me multiply both sides by, whoops, by this. So let me take that and move it over here like that. All right, so basically all I did there was, here I'm dividing by 365 squared. So here I multiply both sides by 365 squared, okay? And this number we can work out on my calculator, or on a calculator. And what is that number equal to? If I can copy and paste it, it's equal to this number right here. Okay, so that's equal to RA cubed. And so I guess you have to know how to do cubed roots. So RA here is equal to, so if you have, let me write it like this here. So all I did was just turn it around. Okay, whoops, like that. So if RA cubed is equal to that, then you can take the cube out of here and you can raise this side to the 1/3 power. Okay, so I don't know if you know this, but like basically when you take the cubed root of something, that's the same as raising it to the exponent 1/3. All right, so if R cubed is equal to this, then R is equal to that number cubed root. All right, and if you put that into your calculator, that turns out to be equal to this number right here. Okay, so RA is equal to that. Now, what is this number? Well, this number you want to compare to the radius of the Earth, and the radius of the Earth we said was 1. So that's what we're doing. We just said, you know what, all we want is a comparison. So you say, well, how much bigger is that one? So RA is 0.338 bigger than RE. Okay, or as a percentage, you could say that RA is 33.8% bigger than RE. Okay, and that answers the question. All right, so over here I said, answer as a percentage. I did that to just make life easy for us because, if you have the radius of the Earth is 1, well then the radius of the asteroid is 1.33815. Okay, that means that the radius of the asteroid's orbit is 0.338 bigger. I rounded off here. I just dropped the 1.5. Okay, I just rounded off there. Okay, and that's how much bigger it is as an absolute value. Or if you want it as a percentage, it's 33.8% bigger. Okay, so there you go. That answers that one. Let me see if there's any questions with that one. I'll give you guys a second. There's that delay, which so I'm gonna have to wait. So any questions with this? Else we're done. Let me know if you guys are okay. So I didn't get to an energy problem. As I said, I just don't have time to do that in the class. But if you want to see an energy problem, tomorrow you can just jump into any one of our Physics 101 lectures. Okay, I'm going to do an energy problem there. All right. So I'm not seeing any questions. All right, Tim. Okay, guys, I'm gonna cut the stream right here.